It looks like sustainability is such a overused term that people feel like, oh my God, I have heard anything on sustainability. So if we start to call it thermodynamic, we may have a better impact on people. And I will just explain a short how I define it. Sustainability means for buildings and cities. Then our approach, you have seen already some of this for Thomas, and then I'm trying to explain 3 projects. Let's see how far we get. The first one is a school, design school in Essen. We did with Sana. Masdar City, you may probably know, that's this first carbon neutral city approach in Abu Dhabi. And then the Ansa Hospital is a hospital we did in Rwanda, which is not yet built, but conceptual work on it. Okay, so defining sustainability for buildings and cities, we put definitely the people first, which means we first said, okay, our approach is to deliver high comfort for indoor and outdoor spaces. And I had an interview this morning where as well I kind of mentioned why as well outdoor, because we are using more and more indoor space per people. So the numbers for Paris, for example, they started in the 60s with 25 square meters per person. Today they are at 45. For 2030, they're expecting everybody needs 65 square meter living space per person mean value, which means the city is dying out because there are less people in the city. Everybody needs more space. They all have a big refrigerator, which means they only have to go out once a week. They're living in their lonely big apartments. The city is dead. The people are not yet dead, but kind of lonely. So in a certain way, it looks like if we squeeze them back to 25 square meters, it would demand them to go out. And therefore, the quality of our outdoor spaces, the quality of our urban spaces, in a certain way, there's a demand for this. Because if you have to spend more outside, and we know if you would do this in Marseille, that's much easier than you do it in Paris, because Paris can be quite chilly in winter. So I think that's why outdoor comfort is as well quite interesting in respect of a sustainable approach. So, and this kind of comfort we are looking for is the kind of the range, thermal comfort, visual, acoustical comfort, in a certain way, how you're reacting on your surrounding. It's definitely as well, I didn't call it air comfort, I call it typically more called air quality, but as well social quality. I listed it. Now we are not kind of people working in the social field, but in a certain way talking about densities in cities. If you, on the other side, it's known if people live in too dense cities, in a certain way social conflicts are growing. So in a certain way, if we want to have this approach, let's say, of energy efficiency and sustainability to squeeze people closer together, that's as well something we have to think about, how the social quality, how's the mix in groups work, that in a certain way we ensure that this is not creating a problem. And then in a certain way, in the second step, we try to do this with the lowest impact possible. And often sustainability is totally reduced to energy, but energy is only one resource. And you see, it's the emission. That's our biggest problem. And it was quite interesting on a conference last week in New York. One of the advisors of Ban Ki-moon said, in a certain way, we are all fine. Fossil fuels were great in the last 50 years to develop our world. But they created one problem, that's the pollution, and that's the greenhouse effect. So in a certain way, he didn't say fossil fuels in general are bad, but he said the side effect that they're putting CO2 in the atmosphere and that this kind of heating up our planet, that's the big problem we have to face. So that's one, and then the surrounding qualities, and if you, in a certain way, go to certain cities, Beijing is a quite nice one, or a good example, and Ulaanbaatar, I'm just working on at the moment. The air qualities in this city is so bad because most of the energy for this regions are coming out of coal plants, power plants, and so the kind of the pollution, the air quality in the cities is horrible. And I think that's as well. And then the resources, as I said, energy, water, depending on where you are on this planet, water can be a quite important resource, land, and then materials. If we know that 50%, oh no, 75% of the copper resources of this planet are already used. And if we use it as we use it today in 35 years, this is all gone. So there will be no more copper, or, and that's where they then talk about urban quarries. You have to go back to cities to, in a certain way, dismantle buildings and get the copper out of the old cables, in a certain way, recycling or reusing this cable. And this is as well, and some of you may be familiar with the guys, Baumgarten, who defined this, that there is no waste. He says there is only material. And this is the cradle-to-cradle principle that he says, in a certain way, the material is always there. It may change in use, but it's important that we are not defining waste, because in a certain way, our our planet cannot provide so much material 8 billion people in a short time period will demand. Finally, as well, low impact as well on transportation, because that's an important aspect as well to look at. So it's kind of and it's clear, we here at Transsolar are often not experts in all these fields. This is why we see us clearly as a member of a team. A team, if you, and you will see it in a minute on the urban design, we work with transportation experts, we work with infrastructure experts, even with water experts, kind of landscape architects, urban designers. So in a certain way, it's a big team typically working on this kind of, and then it's clear there's a certain recirculation between the impact and the quality. Now, this is interesting. This is an evaluation a German real estate company did in respect of what is the benefit or the effect of a green or sustainable building on the market value. Because often people say we are spending more money to build a better building, a green building. Now, what is the repay? And I think it's quite interesting as well, being on the European and partially as well on the American kind of ground. The European philosophy in respect of sustainability is more, I think, a moral-driven approach to say, okay, we have to think about there are limited resources, we cannot behave as badly as we are doing, we should change. And then I think the majority of Europeans then is expecting that their government is defining a rule they should follow, so it all gets fine. In America, it's moral, the dollar is the moral value in this society. So in a certain way, their interest in respect of green buildings was always, okay, we have to find out, when it became en vogue to talk about green buildings like 15 years ago in the US, the first point was Lawrence Berkeley Laboratory did a research on, in a certain way, the effects of buildings with a better performance on the people in the building. What kind of economical benefits it had. And I think, and this is now, and they came to similar effects that, for example, today, this is now, they evaluated a bunch of buildings, 600, you see, 650 real estate projects were evaluated. They typically get 13% higher rate. So the question is now, what they would define as a sustainable building? I think that's a point for as well a definition to say, from what makes this building or this building where we are, is it a sustainable building or not? Maybe depending on the user, it becomes a sustainable building. So typically you get 13% higher rate, and if you get it on the market, you get up to 10% more market value. Typically, the American evaluation for green building is that you spend between 5 to 7% more investment to get a higher performance building. So in a certain way, you get a quite good payback, or at least it increases as well your market value. You have around 30% less operation costs, which is quite interesting if you get tenants in your building, because they are running it on a lower cost. I think that's a big point, and I think Thomas probably mentioned it yesterday for Manitoba Hydro. People are more satisfied with this building, so it's a better working environment, which I think is as well important, because we build the buildings for people to live in, to work in there, and hopefully be comfortable. And this kind of higher contentment leads typically to a 5% higher productivity. And this is what the American CEOs then think is quite interesting, because if they get a better working place for their guys and they got for the same salary more out of them, that's a business. So I think that's quite interesting. Okay, it's interesting to have it in mind, I would say, and this is the European number. The American number even partially goes up to 15%. Having in mind that their typical office can be even in a basement without any daylight. Now, if you put this guy at a facade, I would think your productivity can easily raise 15% because you feel much more comfortable at this. So I think that's something to have in mind. I probably have seen this. So we see us as a player in a team. Some architects, they want to be at the top. I think that's my rearranged one. I had another one where the architect was not on the top. I got a comment from Peter Zumthor. Some of you may be familiar with. He got the Pritzker Prize in 2009. So quite known Swiss architect, but a big egocentric. So he wanted to be up there above the team. But this is kind of how we see us. We see us really as a player, as well exchanging coordination information in the team. And we are definitely not an expert in building physicists. We are not an expert in structural engineering. We are an expert in climate engineering. And maybe the information exchange necessary between the different disciplines to make sure everybody is aware that if he is changing one parameter on his side, he may be not aware, it may affect another discipline in the team, quite important. And I think that's as well important to kind of push the sensitivity in a team, that it's really important to exchange this information to get people on the same level. Probably, I don't know if Thomas showed this, so if we approach a building in respect of indoor comfort, there are different aspects. It's not classically the air temperature, which was the definition, but it's more like the operative temperature. So this is the temperature you feel, which has a lot to do with your surrounding surface temperature. And if you go even into the American code, they talk about room temperature. And in the room temperature, if you look it up in ASHRAE, they mean the operative temperature. It's not the air temperature. Only a lot of people misinterpreted it as the air temperature as an approach. And then your outdoor connection, interesting here. For example, there are kind of research done in Germany that if people are able to open their window, your acceptance in respect of room temperature and room humidity is much more open. So you accept higher humidities, you accept higher temperatures. And if you go down to Stuttgart, in the center of Stuttgart, close to the main train station, you get like 20% higher rent, or you have to pay 20% higher rent if you have an office with an operable window compared to a building with a sealed facade. If you tell this, the guys in America, they say, we can't believe it, because there, for a sealed facade building, you get more, because the users cannot misuse it. That's their kind of definition. That's quite where it becomes, in this case, they say we have to rule people not to be able to open the window, just don't give them a crank to open it. In other parts, they think it's more the value of the market which drives it. So this kind of aspects we have in mind, and then I think a lot of our approaches, and I think that's something as well you probably will learn in the next weeks and months, is we are typically thinking back on basic physics. Basic physics, and that's why a lot of people here are physicists, like conductivity. So this is a piece of concrete. We love concrete because it has a high conductivity. In the same time, it has a high thermal capacity. So you can store a lot of energy in it, but you get it easily in and out. If you take, for example, wood, so your thermal capacity of wood is the same, nearly the same than concrete, but the thermal conductivity is like factor 10 lower. So to charge a big piece of wood and discharge it will take 10 times more time. So in a certain way, this is why it doesn't work in like in a daily circle. Convection, cold air heavier than warm air in the approach for like displacement ventilation. Stratification, I think important, and Thomas explained the cloud yesterday. Humid air is lighter than dry air, so it rises up, which in big spaces, for example, is quite interesting, like Bangkok Airport. 30-meter high space, we're only conditioning the lower 8 meters with cold and dry air. We don't care if there is 60, 80% humidity up there. The only point which we were a bit nervous there, the Thai people ask us, but what is happening if it starts suddenly to rain? Would it rain inside as well? Because if you can imagine, you have 50-degree air, 80% humidity, and you cool it down, it may create some rain. So we introduced some ventilation flaps at the top of the roof. So depending on the flight schedule and depending on the indoor temperature, from time to time we open it up and push the hot and humidity out. Evaporation, transmission, and heat radiation, that's as well a big point and aspect we love to think about, that in a certain way the droplets on the grass is happening because in a clear night the sky is around 15 to 20 degrees colder than the surrounding air, which means any surface here is losing energy in the range of 100 watts per square meter to the sky by radiation. Now, this means this poor grass not connected to the ground gets colder and colder and colder. Finally, it reaches the dew point, you get dew, or if it's cold enough, like 2 days ago, you get rim, so you get ice. And this shows the potential. And if it's interesting, if it's windy, if it's clear and windy, you may not get dew, because then the air is pushing enough energy to the poor grass from the surrounding air to keep it warm enough not to drop below dew point. So this having in mind shows us in a certain way potentials of this long wave radiation. So we are always as well exchanging radiation with our surrounding. But as well, this is a source to think about indoor, but as well outdoor. And we just did a project in Los Angeles where we kind of introducing what we call lunar collectors, which is a photovoltaic element which has copper pipes on the backside. So at nighttime, this black surface sees a lot of the sky, so it may even cool down below ambient. So that's a big source where we can reject heat into the sky. So I think that's principles we have to have in mind and then think about how we can apply it. And from time to time, we are facing the problem that we kind of inventing, I call it inventing a kind of a concept, because we say physics tells us this would work. Now, and then a client comes back and says, okay, where can I buy the product? And second, how many buildings they did and where I can go and see it. And then you have to tell them, there's none, you are the reference. So, and this can make a client a bit nervous. You have seen this, that's then our tools, simulation, temperature, airflow, and light, where in a certain way we are then, based on this physical principles, are evaluating our concepts, which takes a part of our time. And then from time to time, we are even using one-to-one test measurements, because if you build a big building and you're proposing something and it wouldn't work, some clients feel much better instead of just seeing a fiber curve. Makes them nervous to be able to walk in a space which is representing the concept they would get at the end and feel like, okay, looks like it can work. So it will not give them 100% kind of security, but a certain much better feeling. So jumping into the real projects, this is a project in the middle of Germany. This is an old, what is as well interesting in respect of sustainability, this was an old coal and metal iron mining site. So the center in Germany in Essen. This is a UNESCO World Heritage. This is where they kind of changed the coal into cokes, which is a special kind of coal which you can run on high temperature for getting the iron out of the ground. Now this is an old mining site. They digged for like 85 years. They digged for coal. The Ruhrgebiet is like in the center of Germany. This was our main kind of industrial kind of ground where they digged and where they produced steel. Now, they digged for like 85 years. In 1985, they closed this mine. Out of political reasons, in a certain way, it it was cheaper first to import coal, it was cheaper to import steel, so the German coal and steel industry nearly died out. This is still, the whole region is still struggling because they lost their main industry. Now, and then they started to do new activities there. So one is to, in a certain way, to do education there, and there was a competition. That's the team. Sana stands for Seishima and Nishizawa, two architects from Tokyo, and there was a local architect, Bollinger Grohmann, the structural engineer. Transplan is a Transolar daughter. You will, Ekus, no, he's not here. We have a kind of a daughter company which does kind of technical general planning, coordination, trying. We did the climate engineering, an MEP engineer, and the building physicist. So that was the team. They won the competition with a block. The building is 35 by 35 by 35 meter, so it's a perfect square. It's kind of 300 meters from the old shaft. Now, what is interesting, in '85, this is where they went down to minus 1,000 meters. This is how deep the mines are in the Essen area. And in a certain way, they stopped it, but they decided out of political reasons, because all the mines are governmentally owned, to close it, but to keep it dry. Now, to keep it dry, and I'm jumping over the weather in Essen because this is a bit, that's a boundary condition to think about. But I think this is the 1,200 meter down there. Now what they're doing, they're pumping permanent, they closed it, so they're not digging, but they're pumping permanently, day and night, 24/7, the mining water out to keep the mine dry, to maybe in 10 or 15 years decide they would go for coal again. And if they would flood it, it would be a bigger mess, certainly to get it dry again. What is interesting now, okay, and they're pumping out, to give you an amount, around between 300 to 600 cubic meters per hour. That's a big amount of water. Now this water is between 28 and 35 degree water. It's warm. And it's heavy metal loaded. What they do, they pump it in the next river, which in the first moment you can see, give me a break, it can't be. They pump it in the next river. The Emscher is what I would call a public cloaque in Germany. 15 mines are dumping their mining water into the Emscher. Before the Emscher goes into the Rhine, there are 15 water purification stations to get the shit out. And this is working day and night and will work for the next whatever, how many years. Now, you think in a moment, and this is quite interesting because this was coal they closed digging like 30 years ago. Now, what is interesting, they say, oh, why don't we stop pumping? If maybe political reasons, they find a new energy source, whatever, fusion reaction or whatever, the water would fill up. What is interesting to have in mind, the whole Ruhrgebiet dropped between 20 and 30 meters in the last 100 years. Because of getting the coal out and the iron out, the whole landscape dropped. Now what is interesting, if they would get the water up here to around 200 meters, the ground would start to lift. And there's one mine close to Aachen, close to Cologne, where they did it. And there's one little village where through the village, through the streets, through the houses, they have a shift of like 10 centimeters in 1 year because the ground kind of lifted up uncontrolled. So infrastructure-wise for buildings, this would be a total disaster. That's why all the mining companies had to, in a certain way, to put millions and millions aside. By the way, the electricity for this pump is for one mine, €1 million per year. 1 million. For the next. Now, they need to repump it to prevent that it cracks up. And they have to do it forever. Either they take into account that the buildings and infrastructure gets lost, or they need at least to start to pump at a height of around 200 meters. So that was for me a kind of, I didn't know this before we got into this job, that this is quite interesting, that in a certain way it shows for me that people dig for coal to get an energy source, but they're not aware they're opening the box of Pandora, and in a certain way, this will be there forever to handle this. And there are more other energy, and don't step into other energy fields, which may be even more critical. So energy-wise, this for us was a great source. We said, why we are not trying to use it for the building as a heating source? So in a certain way, okay, displacement ventilation, get the air in, and then it was the ceilings, because they span 24 meters without a column, because Mrs. Sishima didn't want to have a column in the space. So they are 0.5 meter thick. Now, to have not 0.5 meter thick concrete, which would be a lot of dead weight, they put what is called bubble deck. They put hollow core elements in which take out around 35% of the dead weight. Now, we put like little plastic tubes in to activate the ceiling as a source, and if you pump water through it, it would work. It works as a nice heating device. That was one application. And then reflecting the German code, and this is now American units, so structurally they would need around 25 centimeters of concrete to have a 35 meter wide concrete wall without any expansion cracks, because the architects are quite minimalistic architects, so they didn't want to have expansion tracks, and they wanted concrete at the inside and at the outside, which together with a minimal German insulation of around 10 centimeters would be nearly 60 centimeter thick wall. So you saw the little windows they had in, the windows became holes because they were deep as wide. So, and they were totally unhappy. So they said, can we reduce the insulation? And I said, I give you 2 centimeters, it wouldn't help. So finally we said, okay, let's invent something which is called active insulation. So it's now a 12-inch monolithic concrete wall without any insulation. It just has plastic pipes in it. And we are pumping the water, the mining water, through the pipes. So we're heating the wall as the building would be insulated. So we're heating it that the inside surface temperature stays at around 16 degrees or 17 degrees, as the wall would be insulated with a 10 centimeter insulation. It's clear we are losing like 80% of the heat we are losing to the outside. Only in a certain way, okay, we are limiting the inside heating losses, but it's clear we are losing a lot of this free heat. But I said, before pumping it into the ampere, why we are not using it for the building? Now, what was interesting as a side effect, we saved like 1.5 million in investment because the double shell concrete wall was much more complicated to do than a monolithic concrete wall with some pipes in it. Some pipes, I think the contractor as well, kind of. So this was an example exactly where they asked for the reference. I said, no reference. We can show you that we think it should work. Make sure that if a pump fails, it doesn't break, whatever. So it was a big hassle. But we got it, convincing them, got them built. Finally, the loops are not looped like this. They are open at the end. So in case of a pump failure, we can open a flap at the end and get all the water out before the wall freezes and would break up. So that was kind of some safety. So then this is the layout, how the pipes go around the window. So this was I think this was then in reality. So for the concrete guys, that was quite a work to do all these pipes embedded in this monolithic concrete wall around the windows were the most important. So, and the building we're growing up, that's the pipes below in the 0.5 meter thick ceiling where then the bubbles come above in kind of cages. And then you pull the concrete, you pour the concrete above it. And this is where typically, and you see there's a little manometer, a pressure control, because you are pressurizing the pipes during the concrete process to make sure in a certain way they get the maximum stability, and you can always suddenly kind of find out if you have a leak in the system, which as long as nobody drills in, we seldom had. So that's like, this is where the pipes come out from the floor below. We typically have a raised floor, so you can connect to this kind of embedded system. The concrete is all exposed. So you see, finally, they got 2 columns, but not as many. So that's finally the finished building. This is the pipe which comes from the mining site. This is the building. What is interesting, the upper, like say 8 meters, is just a roof terrace. There is no more program. It's just to fulfill the square to a square and there's not even a roof, there's only a partial roof above it. This is typically the office floors, and then there are 3 floors of academic program. In the building, this is kind of the connection looking from inside. This is our kind of connection. This is the old mining shaft. So this is where we get the heat from for this building. The 12-inch, so the 30 centimeter thick wall, which is still 30 centimeters, but compared to, and there are smaller windows, it was quite minimalistic. Inside, the flush windows, flush to the inside, we said, okay, we need a shading because still we have around 30% openings on the facade. So we got a curtain, which in a certain way has like 10% transmission. So this is enough for, in a certain way, keeping the heat out and getting partially some light in. This is the upper levels of the offices. We insisted, which was a kind of a discussion, aside of the mechanical basic ventilation, we have motorized operable windows. What is interesting, the first year when they operated the building, the control system, the mechanical ventilation didn't work. So we were fully relying on the operable windows. We were so happy we had them. Even the architects finally were happy that we had operable windows, because without it would have been a much bigger disaster. Now, you see the curtains in front of the wall, so this is where they're storing. Now, what is interesting, in summertime, you can imagine if you don't insulate the wall, the concrete has a certain absorption, so the concrete heats up. So after a 2 or 3 week heat period, you make, in a certain way, the whole capacity will charge and it gets warmer, and maybe finally you will get the warm to the inside. So what we did, we're using the pipes. Now, this is interesting. This is our little kind of evaporative cooling device where we are spraying water on a heat exchanger, running the water through, so we get down to the dew point. Not to the dew point, to the watt bulb. So, and we are using this water, then piping it through the walls to, in a certain way, to cool down the walls in summer case. What is interesting, this is the big recooling tower they built for the mine. For the mine, they always had to cool it, because down there in 1,000 meter, if you wouldn't cool it, it would be always been 35 or even more. So it's a kind of reminiscence, a kind of reminder of the old technology now being modern interpreted to operate the building. That was another very interesting side effect of the building, that talking to the local people, they felt this is such a unique local concept, which in a certain way reflects their tradition. And if you talk to people in the Ruhrgebiet, at least their father or their grandfather or their uncle had been working in the mines. So working in the mines still has a quite high value. So what our concept is doing, we are using the last remains of the mines, which is the hot water coming out to, in a certain way, to support a building at this site. And it's clear you can't move this building from the site to another place. You wouldn't have the mining water. So it's a quite strong local identity this building creates for the site. What was interesting, we created the heat exchanger to the mining shaft, and in a certain way, by doing so, now we have enough spare capacity that follow-up buildings will, in a certain way, can as well tap into it. We spent $500,000 for the heat exchanger, titanium, which was a big discussion. When would it fail? Because you have clocking, whatever. Said, this is a mechanical engineering problem. You have to be able to clean it. In worst case, you have to replace it. And they said, yeah, but where are the guarantees? I said, we have no guarantees, but we can engineer it at the best to make sure it works. Until now, after 7 years, exactly, 7 years of operation, there had been never a problem with the heat exchanger. You have to clean it every 4 weeks. They are pushing this kind of little kind of round balls, which is like a brusher, through the heat exchanger in a certain way to clean the assemblies on the heat exchanger pipes from it, and that's it. So I think that's as well a kind of engineering. What is interesting, not we, but other people did a check on it. Unfortunately, it was not very cold. It was only 10 degrees. So they did an infrared kind of picture. And what you can see in a certain way, that the areas where, this is where, in a certain way, it gets colder. This is the roof terrace. So the areas where you have the active insulation, even to the outside, is warmer because it's pushed from inside. Now, as well, looking at From the inside, what you as well can easily read is the warm ceiling, which is kind of your radiant source, and then the walls are tempered to stay in the range of, in the corner, it's clear, you get the heat conduction maximization, you get more losses, but then at the surface you stay in the range of the room temperature. Final picture, the curtain. Now, we are aware that a curtain, an inside curtain, if the sun hits it, gets warm. Now, how you prevent that you don't feel close to a radiator? And this is now about radiation. If you put a kind of metal coating on it, a so-called low E, a low emissivity coating, because physics tells us the heat radiation coming out of this surface is proportional to the emissivity factor, which is a material property. So we said, if we do an aluminum-coated curtain at the inside, it may heat up, but the warm air would typically rise and be exhausted with the exhaust air. But you sit here at the table, you don't feel it, that the curtain may have 30 or 40 degrees, because by the low E coating, you cut down its kind of property to emit the heat. What is interesting, in the infrared picture, low E, because the transmission is 0, becomes as well a high reflector, because absorption plus emission plus reflection has to be 1, the Kirchhoff-Gesetz, the Kirchhoff law. So what you can see here now, in the curtain, you're reflecting the warm ceiling and the warm shaft in the middle in the surface of the curtain. The curtain is not as warm as it shows in the picture, but it reflects just the warm ceiling being reflected in the low E coating, which doesn't emit. But if something doesn't emit, it becomes a mirror. It becomes a long-wave mirror. And I think that's quite a quite interesting picture to look at this. If you see that then suddenly the curtain, even in winter, would provide a certain increase in comfort, because you wouldn't see the cooler wall, which is 20, but you would see like more a surface of 23, 24 being reflected from the ceiling in the curtain. So this is, some of you may have seen this book. It's a good book. We have both books here. This is the first round, and then they did like 2 years later a green one. The School of Economics in London. They called it The Endless City, by kind of evaluating, let's say, the values, mainly the statistics of cities. And I think in the first book they had like 10 or 15 one. In the second book there are another 10 about density, about criminal rates, about what life expectations, a lot of about energy, about air quality, all this stuff. Because they said we have to collect this material, because in 1900 we have 10% of people living in cities. Now we're approaching, in 2007, it was more than half of the world lived in cities. Until 2050, it will be 75%. The question is a bit, and I think that's something to question, what is the definition of city? Because if you go for the German definition of city, today we have 75% of the German population living in cities. So the question is, where is the range of city? You start a city from 1 million, or you start a city from around 100,000? I think that would be a question to ask the guys, first to say, where is your definition for the sentence? Now, that was for us a background to think about, or we got the invitation from Foster and Partner to do this. It was first a competition for the first zero carbon footprint city in Abu Dhabi. And you see, this is the team. So Foster and Partners for Architecture and Urban Design, Traffic, Systematica, Infrastructure, WSP with the Energy Concept, MEP, Flack and Kurtz, and Solar Systems, ETA. From Florence, there was a landscape designer. So it was a big team working on this. And the approach was to say, okay, this is Abu Dhabi today. What is interesting, this is Abu Dhabi in 1960. This castle is right here. There was nothing there. There was just this little castle and sand and some little fisher huts. So they changed in this kind of 45 years, 55 years, 53 years, from nothing to a city where you can already read a grid. Most interesting one, this is exactly the grid of Manhattan. So they copied one-to-one the grid of Manhattan to Abu Dhabi, which means you have an avenue which is 75 meters wide. Now, I can tell you to cross an avenue in Abu Dhabi when it's 47 in the shade outside in the sun where you face like 60 Celsius, 75 meters, that's quite long. You nearly don't reach the other side. This is why the Abu Dhabi people, they use a car to cross the road. They drive with a car to the other side of the road to make sure they don't get a heat shock. So I think this is an example where you transfer an urban design into a total other climate, ignoring everything. So, and they said, okay, this is Masdar City, close to the airport. If you've ever been in Abu Dhabi, this is the existing airport. There's a new airport by KPF under construction here. So this is Masdar City, a site of around 600 hectares would be donated to show the world that you can do today a carbon neutral city. The background of it was in 2004, they were blamed, the UAE were blamed to be the worst guys in the world, to have the biggest kind of ecological footprint. The WWF, sorry?
I mean per capita. Like
per capita, exactly, per capita. So not in total because they are such a few. The Chinese would always win. So, but in this case, per capita, exactly. And in a certain way, the WWF does it every year to count the ecological footprint per capita for each country in the world. So in 2004, they got the red line, red light. Now, what is interesting, this is now reflecting a bit the kind of the Islamic culture, that they felt much more blamed, not because they have this kind of belief, but because Sheikh Zayed, who was the dad of the existing emir, who was the founder of UAE, he told them in one of his, in the Islamic culture, there's the kind of what your forefathers defined for your and for the future is quite important as a rule. So he defined one of his rules was, treat your country as your forefathers did and respect in a certain way the habits or the potentials of the land for the generations after you. Now, being blamed to be the worst guy in the world didn't fit. So they felt like really squeezed. They said, okay.
He said that because he had some references from the Islamic, from Quran.
Yeah, maybe. I didn't, maybe that's a good point.
Right now, they are sometimes promoting Masdar City with some quotations from Quran.
Yeah. Yeah, no. I can. There were like in this kind of first exhibition on Masdar City, there were like 10 of his main sentences, and one of them were really strongly about the environment, and maybe he even used parts of the Quran as a. But this was the impression. They said, okay, guys, we can show the world we are the bad guys, but we put $25 billion into this. We show the world that. If you do it on a long term of 30 years economical payback, you count it on 30 years economical payback, you can today build a carbon neutral city and make money out of it. So that was, in a certain way, the intention. What is this? Well, interesting, what we always discuss with the guys, it was so obvious that they said, if Masdar City becomes a success, Abu Dhabi is ready to build 50 Masdar cities in the world. Because this is what they would invest their money. Because the final payback was in the range of 6%. 6% was the annual payback of the investment. So they said, if we run this with this is the best investment, no bank would give us a guarantee of the next, and energy prices may rise. So that was a kind of even a kind of economical model they were thinking on. It was not only, I think that was a quite clever point to say, okay, we show the world we can do it. Aside of it, the intention is to build the biggest research hub in respect of renewable energy components. So this is the research center for the world for any renewable, that's their vision, for any renewable energy components. And they do, I would say, our politicians, the Germans should, or even the Americans should be alarmed because someone is putting 25 billion into a research lab to push, to get the sources. And if you, for example, if you know that Mercedes-Benz here in Stuttgart, their engine development for the electrical engines for the future are done in Masdar City. So in a certain way, it's already happening that big companies are already deciding to go there, hopefully to get good researchers, good and it's a taxless so tax-free, a tax-free zone aside of kind of this basic investment. Now, what is interesting, something I never, at first when I was there quite often, didn't understood. So, okay, they changed in this 53 years. They changed from the tent to the high-rise. They changed from the camel to the SUV, and having in mind that originally they lived in Abu Dhabi only half a year because they were pearl divers. In the UAE, they were pearl divers, they dived, but in summer it was so unbearable, hot and humid in Abu Dhabi that they traveled 7 days with the camels to Al Ain, into the desert, because it was better to stay in the desert oasis than to live in Abu Dhabi. So they did like people migration. Every half year they moved back and forth. And they lived on a quite, let's say, low calorie kind of diet. Now they eat everything. What is interesting, now today 33% of the Emiratis are high diabetes thick. This is the country with the second highest diabetes rate in the world. So there's a little island in the Pacific where it's higher, but then the Emiratis are the next. And you see it if you come from the airport, you are passing like 15 hospitals. And I was always thinking, what do they want to do with all these hospitals? Do they want to treat Europeans there? No, they have to treat their own people. So that's quite interesting. And I used to this always, and I just was reading it in the economics in a journal when I was flying there, that in a certain way, you can change in a certain way your habit, but you can't change in a very short period your body. So their bodies, they can't follow in a certain way the changes in their life pattern. I'm sure in 2, 3, 4, 5 generations, they will be there, hopefully. But it's kind of an interesting point to see that how, in a certain way, we change in a 2 generation. This was a 2 generation. And I always, my conversation with the sheikh was always, he said, I can only sleep in a full air-conditioned sleeping room with 18 degrees Celsius under a blanket. That's my minimum standard. And I said, your grandpa slept in a tent at 30 degrees outside, 80, 95, 90% humidity. And I said, so this is only changed in your head. Your body didn't change, so it's only in your head. So if we have to change it back, we have to train you to change it back in your head, that your expectations are different. So I think that's a quite interesting, so that's the starting point. So this was the plain ecological footprint. This was their number. That's the United States. This is Germany. This is where they want to go to. So that shows as well their long passage, that they even beat, like in CO2 emissions, the Americans by far. So to get down, we are at around 11, the typical Germans, and they wanted to get down to 0. So this was as well to make them clear what a challenge this would be. Now, this is the kind of the urban program. So you see around a university which is around 200,000 square meter, they were thinking on big technology park, commercial, so big resources, research units of around 1 to 1.5 million square meters. They're thinking there should be around 50,000 people living there with their families. So around 1.5 million square meter housing, and then a kind of support structure. So in total, we talked about 5 million square meter on a land area, which was at the end, because the sheikh in between gave a donation to a friend of him. So we suddenly lost 50 hectares. So we had 600 in the beginning, and then 1 week we were told last week the sheikh donated 50 hectares to another guy, so we had only 550 left. But compared to the 5 million square meter, you see this is a GOP of like 1. So this is kind of the square meter useful area to the land area of 1, which they think, and this is always the big pressure on Mazda, this is a waste. Because Peter, for it, we did the neighbor plot, and the neighbor plot has similar size, but they built 25 million square meters on the same plot. So more a coverage of 5 instead of a coverage of 1. But energy-wise, this would never work. Okay, so that was in a certain way a good starting point. Then we said, okay, if we take these 3.8 million square meters of conditioned areas, and we take the today consumptions of a typical hotel, of an office, of a housing project, so the typical program, we put it together, and we put all the energy for the city, street light, traffic, desalination, distribution into account, we were at 1.8 million megawatt hours. Now, if we would have covered the whole site with photovoltaic systems or with solar systems with a 10% efficiency, we would only be able to get 50% of this production. So it was so obvious that if we don't want, okay, we can get it down to half, but then the message would be living in a carbon neutral city means you have to live in a solar plant. If that's nice or not, something to discuss. We said, but this would be the wrong message. So we said, we have to get this much further down to be able maybe to cover only half of the site. So, but this made as well clear that energy efficiency, which is well in respect of economy, the much better kind of step, is the first step to do. We have to get the loads down that we are consuming less, and then think about a substitution. Now, just a short where we are. Now, I was not so familiar with we call it, in Germany we call it typically the Persian Gulf, but I learned it's called the Arabic Gulf. If you do it in Abu Dhabi, you better say the Arabic Gulf. No, this is not the Persian Gulf, no. Because Persia, Iran is just here. So what is interesting, it has just this little political connection, Strait of Hormuz, to the Indian Ocean. Now, this little connection makes this a much special as well ocean, because you have typically only a depth around 30 meters. This is a very shallow sea. And by this small connection, the salinity of the Arab Gulf is typically 30% above the world oceans. The world oceans are in the range between 33 and 35 ppm. The Arab Gulf is today at 45. What is interesting, marine life, like the corals and the kind of, what are the trees? The mangroves, they die above 50 ppm. So already the mangroves in the Arab Gulf are like only growing up to 8 meters high. If you go to Australia or South America and look on the mangroves, they grow up to 30 meters. So the salinity already kind of squeezed them down in height. So it's a quite special, and because it's so shallow, it gets really hot. So this gets in summer really up to 35 degrees Celsius. On the other side, in winter, it cools much further down than the Indian Ocean. So this is more like a big lake. Now, what is interesting, which has to be, and we didn't know, when we approached this, I had no clue on all of this. So that's all what we learned. And I think that's quite interesting that doing this kind of thing, you have to approach it so holistic. Because in the first step, okay, getting Abu Dhabi fresh water, it's not raining a lot. So you get it, you say, oh, perfect, we have a lot of sun, let's do solar desalination. You solved it. No, you don't solve it, because you're pumping back high saline brine into the Arab Gulf, which everybody does around the Arab Gulf, which already led to a 2% increase in salinity in the last 20 years. Because everybody is dumping the high salt into it. So this kind of led us into a thinking that we have to be, for this little city, we have to think about how this Arab Gulf works in its old surrounding, changing the performance. Okay, so looking on the solar, okay, where's the sun, where we are, the sun quite high, coming right from the zenith. In summertime, you have quite a good solar, close to the maximum. I think the maximum on our planet is close to 2,500. So that's a quite solar beneficial site. What is interesting, the mean outside temperature is 27 Celsius, which is in this case, not only in this case, as well the soil temperature in a 10-meter depth. So if you go here in Germany where we have 9 degrees Celsius, you drill down to a depth of 10 meters, you find 9 degrees. Because you can imagine the outside temperature does like a sinus curve, and the ground at a certain depth is just following less and less and less, and finally it exactly hits the kind of the mean value, which made us clear this is not a big source for natural cooling, because if you dig down to 27 at 47 outside is still cool, but not to drive like an air conditioning system. And we had like 5,000 hours above 11 grams, so it's not only hot, it's as well very humid. So that is what we call the hourly fiber curve of a site. So this is the hourly temperature values of Abu Dhabi, where you see, and this is temperature in the shade. That's not in the sun. So in the shade, you get up to 47, and if it gets to your cool night, the cool nights are in the range between 28 and 32. So that's in a certain way what you are facing. That's why they left Abu Dhabi in summer, because it's typically not the nicest climate to stay. So in winter, in so-called winter, where you get at daytime 25, at nighttime, this is like our summer. You missed, and you will get it next year. Okay, hopefully a good one. So in a certain way, that's what you are facing. So that's something we had to have in mind. There are some changes, but as well, looking on the city, nighttime temperature of 30 degrees are still quite high. Wind, which is interesting, is typically coming from the northwest. And the northwest brings it right through the Arab Sea, which means, that's why I mentioned the high temperature. It's then crossing, because typically this is the wind which comes from Iran, from Persia, which is a continental wind, which in Persia is perfect, dry, cold. They have this evaporation cooling effects. They build the wind towers in Abu Dhabi and in Dubai. This wind is hot and humid. So because it collects all the humidity from the Arab Gulf and gets in addition the heat. So you get 47, at a hot day you get 45 to 47 degrees Celsius wind, which has a humidity in the range of 45 to 50%. If you cool this down to 25, you're far above 100% humidity. So I think that's a source where we said, okay, having this in mind, our city has to be able to respect kind of that. We looked on how is nature surviving in such harsh climates. So the Donka gazelles, for example, they are a local species living in the UAE. They can survive for months without drinking because their kidneys, so their system, our kidneys, you know, we have to drink like 1.5 liters of water to flush them. They can survive without any water, just the water they collect from the wet grass. It cools down to 30 degrees, so at nighttime you're reaching nearly to 100% humidity. So what the guy does, he puts his back to the sky, cools down his back, gets condensation because he has a high hygroscopic coating on his back, which as well has the lotus flower effect, which means the droplets are not distributing, they keep in droplets. Then he lifts his back, gets it in. That's the day of the drink. The drink of the day, the drink of the day. So this is, he survived for the next day from this water droplet he collects in the morning. And it's quite interesting, researchers at MIT developed a facade coating, kind of copying the performance of this guy and saying, if we apply this, for example, to a triple glazing or to a double glazing where there's no heat coming out from the building in the morning, we are able to collect water. And if you leave I had this in mind when I left the first time in Abu Dhabi, we left the airport, we were standing in front of the airport, suddenly my sensor was hit by a water droplet because they have like shading lamellas in front of the airport and they have no thermal mass, they cool down by radiation and they get into condensation, and then in the morning hours you see all the droplets on the passage. So that was a point where I said, okay, there might be a source we have to think about. So that's the program finally as well, the layout for the city. Now urban planning is a special chapter. I can't step into it, but kind of as well, a livable city is as well about where are certain programs. So in a kind of, they try to put the university in the middle. The blue is all the 1.2 million square meters of research zone, and then the yellow is typically residential. There's some violet, which is production. We created finally a square which is roughly 1.5 by 1.5 kilometer, so quite big, to be able to have around our 3.8 million square meter program in there. If you come from outside, you have to leave your standard car in such a parking. The round ones are big parking drums. And then you take a little electrical car to go into the city, because we said one finding was we have to build the city very dense. Now, if you build the city very dense, you can't have cars polluting your city air, because that would be kind of, if you ever in summer are in New York, you can find out what car pollution in a street means. Or I think maybe Delhi or other cities in the world are as worse. So I think that was clear. We want to push it as dense together, so it was clear we only use a minimal city ventilation. Because 47-degree city ventilation would be a nightmare because this means your street are at 47. So we said we want to keep it minimal ventilated. So, and it was clear this kind of reduction, that's what I call energy efficiency. So load reduction on one side and then using better systems to provide your comfort should allow us to reduce like 70% of the loads. And then we go into renewable substitution. Finally, you will see in a minute, we pushed it down to 80% because it was quite an effort to still get enough surfaces for the other 30% of energy. Now, it's interesting, if you are in the desert in Abu Dhabi, the air temperature is around 46. That's the maximum. Now, the so-called felt or operative temperature, because you are in the sun and you get facing the hot sand, is 67. Now, going into the city square of Abu Dhabi today, you easily get up to 71 because it's less wind. Even there's a lit wind. Now, if you get into shading, you may drop it down. You get vegetation. We looked on different strategies. Finally, you can see if we want to get it below the 46 outside, we nearly have to, in a certain way, to create a kind of a microclimate of the city, which we want to change it from a heat island to be hotter than outside into a cold island. So that was the challenge we kind of said. This is now the outdoor comfort approach, saying we want to keep this city as cold as possible. This means we have to have very narrow streets. They should be partially even self-shaded or artificially shaded. We need thermal mass to expose. Our 30-degree cold night is a cooling source to keep it at 35, so we can ventilate the streets at nighttime, get the masses down. If we shade them, hopefully this mass helps us. So the next day, and it was clear, we can't get the 47-degree wind in. We have to keep it out. So make us low, keep us low, and hope the hot wind goes above your head, doesn't hit you. That was the kind of the approach. We looked carefully on the orientation of the city.
Isn't this blue line from the previous slide?
This is a photovoltaic, we first saw it on a kind of a retractable shade, and you see it in the animations later, in the really pictures, the photovoltaic, which are placed above the roofs, they are partially cantilevering out. So you get like an overshadowing of the street, combining on one side, you're extending the energy collection, on the other side, you get the side effect. And it was interesting to look at, because we did tons of study as well, because it's clear if you get the streets very narrow, you optimize in a certain way the temperature in the street, but you cut down the daylight. So we kind of, let's say, we reinvented the kind of the North African, you find it in Syria, in Aleppo, you found it in Marrakesh, this kind of structure of the Islamic culture that typically the streets are very narrow and every house has a courtyard. So now, this courtyard traditionally was a private courtyard. Now, how you transfer this if this becomes from a private courtyard into a public courtyard? So there were big discussions how we had to do this to find.
Also, I know that you already constructed a part of the city.
Yeah.
So 35 degrees, is that a simulated number or measured number?
You see it in a minute. It's measured.
Yeah.
We could prove it, even if the example which we could measure it's quite small. So the orientation of the streets we looked at in respect of overshadowing and getting light into the city. So at the end of all our iterations, we find out that the best orientation would be we rotated by 45 degrees to the north. Now, what was very interesting, Thomas' group at the same time was working on a low-carbon city for Toronto. Independent of us, they optimized the orientation for Toronto. What did they find out? 45 degrees rotated to the north for the best orientation for a total different climate. And then you look into history and you look on the city grid of Pompeii is 45 degrees rotated to the north. A lot of old Indian cities are 45 degrees rotated. It looks like that's a rule for our planet, which is a quite optimum orientation.
Islamic Cairo too.
Yeah?
The
Okay.
spine in Islamic Cairo also is.
Okay. So, that's what I always say. It's not, we are not the big inventors. We are kind of the reinventors of what our forefathers already knew. And by inventing the chiller and the fan, we missed all of it because we said, okay, we don't care. We can just use the machine. So maybe we have to learn just some of the old knowledge back. This is interesting now in respect of a city now. In respect of public transportation, if you don't have private cars, you need public transportation. Now, what is the typical distance somebody would walk to a bus stop or to a metro station? So this is MIC, our traffic consultant friends from Milan. So they're typically, this is now for, let's say, European temperate climate. They typically say whatever, so people, this is the acceptance. People would walk, if you want to keep it in the range of 70 to 80%, between 250 and 300 meters, people would accept. So that's how you plan in a city. Now, if you are facing 35 or more outside, the distance drops. Because it's clear you don't be totally sweated reaching then the air-conditioned bus. So that was clear that we would need to have our maximum distance walking from your house or from your office to the next public transportation should be in the range of 100 to 150 meters. Now that was a base for their layout. This is now a little layout, and these are little underground electrical cars you see in a minute. So there are 3 layers of public transportation. There's a metro running to the airport, where it's one stop in the middle of the city. There is a tram which runs above ground, which crosses the city once, and then there are this little, and the dots are the stops for this little electrical cars called PRT, Public Rapid Transportation, and you can, if you want to experience them, they are working in London. One of the outside parking stations has this kind of fully automated driverless cars, which in London has 10 seats. In Abu Dhabi it will have, or they bought already kind of 20 of them. It will have only 4 seats because, as well respecting the local culture, it was clear you should be able that whatever a kind of a woman should be able to travel in her own car. It doesn't have to share it with a foreign guy. So I think that's something we were looking at to be able, and you would go down there and it was clear we couldn't get it on the streets because our streets being up here 4 meter wide, being here at the bottom in the arcades like 7 meter wide. And I think if you look on this section and you go back to Nîmes or to Bologna or to a lot of old European or international cities, you can find the sections because that was something how they developed their cities. So we kind of reinvented it after a ton of simulation. We maybe have looked better in some old books. So we kind of, and it was clear there was no way to get these electrical cars on the street. They are like, you can go there with your bike and even maybe with your Cetric, but not with the electrical car. So they are one level below, so you have to go one stair down. They are crossing here. What is interesting, if they cross the city, there are partially parks which are on the lower level. So you would kind of cross, and you see it in a minute, you would cross these parks really on ground level. And there are sometimes openings where even the light would penetrate down to this area. That was one of my hand sketches. We said, okay, this is the main wind. So what is clear out of our airflow analysis, and Tobias Fiedler, you will learn to know here from our company. He was our project leader on this stuff. He did the CFDs, and we find out if a street in the wind direction is longer than 75 meters, even at an even temperature flow, this air would tend to drop into the street. So we said, these streets are without problem because the wind is just going above it. So we have to limit the length of the streets going in the wind direction to make sure as much as possible that the wind goes above, and then we get a jump, and then the next one. And we recommended to introduce 3 linear parks, which would start at the northwest, which is the main wind direction, and then curve to the east, because sometimes at nighttime you get a cold breeze, 30 degree, a cold breeze from the desert to ventilate the city. So that was in a certain way the intent of this sketch. And in a certain way you can see how they kind of put it then into a master plan. So that's the length of this. Some are longer, some are quite short. This whole city is kind of kept on one level because it's clear if you would have a high rise, it would work like a spoiler. to get the air in. And then, oops, so this is at daytime. We typically get the wind from the northwest. They reduced the parks from 3 to 2. But this is as well where we get the air from. This is where even at 47, 50% humidity, you have a certain amount of evaporative cooling. So a densely linear park can do some preconditioning. So, and there you get the fresh air into the city. You need the air only for feeding people. You don't need the air for feeding cars or production or whatever. So it's only minimized in the amount what would be necessary to ventilate a city for providing fresh air for the people, because it's a heat source. And then at nighttime, the cold wind hopefully comes from the east as well, infiltrating through the city, allowing, it was so obvious that our 1.5 kilometers is far too long to feed the city only from the edges of the city with fresh air. Now, this is a wind tower we are, or typically familiar, we find in Persia, in the today Iran. Now, you find them as well in Dubai, but I think they built it in Dubai as Iranian traders, merchants came to Dubai and built their houses, and they built them as they would build it in Persia, because in Persia they work perfectly because they're getting mostly as well the dry wind, and you can even do a partially evaporative cooling. You ventilate your house. In Abu Dhabi at 45.7, it's not a good idea. So we said, but it's a good idea to put these wind towers at the end of each our streets. So at daytime, they work like a wind shelter for the wind not dropping into the street, because the wind has to go around the street. And then at nighttime, I can open the top and catch as much as possible of the cool air and get it down, push it really into the streets, because making it very tight at daytime makes it as well tight at nighttime, where I want to get the street in. And I think that's quite interesting, using a kind of a traditional building form in a new interpretation, not for indoor, but for outdoor, to optimize the climate in the streets. That was finally our number, 80% reduction. And it was quite tough. There was a big discussion with the client, because some of these efforts are connected to investment. If you saving 80%, that's a lot. So some, whatever, it was clear they would need triple glazing, because with a double glazing, your transmission gains through the pieces of glass were still too big. So that was in a certain way. And what is interesting, if you see all of this, still the building operation is still the biggest chunk in the whole energy footprint of the whole city. But what is interesting, we were able to cover it with kind of half of the site. So that's the layout finally of the city. So we have two linear parks. This is where I mentioned there the little electrical cars, they driving on ground, because the city is elevated, like 8 meters above ground. This is where they come out from this underground, shoot through the green park, and then enter into the next tunnel. This is the street line. This is the outdoor spaces. So we were kind of covering, there's some solar plant at a certain edge, but we were kind of trying to keep a big part of the site in a sort of unused. Because we said, building a city, a such dense city on such a footprint, and it's like, typically, we have like 4 to 5 floor building height, but very dense because we have so narrow streets. So you need a relief, because here you may sometimes feel claustrophobic. So you may have to walk out, and we all know big cities, dense cities have parks in a sort of way to breathe. What is interesting, that was a big discussion with the client, because for the people in UAE, they said, but Matthias, this is just desert, and desert is to build buildings on. And I said, yeah, but this is your nature. You need it as a contrast to the dense city to go up. And they said, yeah, but Matthias, they will kill us, because they will tell us, you can cover all of this with houses. And I said, yeah, but then you will never make the energy balance. So that was and it was kind of interesting, this kind of dialogue of a quality of indoor and a quality of outdoor. Now, what is interesting, it looks like, okay, in such a harsh climate, outdoor quality in a certain way is not so high valued, because they say, come on, at daytime, I don't go outside because it's just too hot. So I think that was another point for us to rethink the urban quality and the outdoor quality. Now, what was interesting, this is our system, a lot of relying on PV cells. We have like 2 or 3 windmills because we are too close. Oops, if I go back a picture, this is the airport. We are so close to the airport, and you have like, I think we have to be below 40 meters here, below 60 meters. Down here at the edge, we could go up to 100 meters. So for a windmill, this is not enough height. We have concentrating solar systems, which can use big storages, but it was so obvious we need to install like 150 megawatt capacity, but our peak capacity for the city is only 35. But we need to collect at daytime because at nighttime there's nothing. So where to store it? And first the client wanted to do an island solution. We said there's no way to do it as an island solution because we can't store it. So in Abu Dhabi, by law, you are not allowed to tap into the grid, to charge the grid with electricity. So they had to change the law. They changed the law in 2 weeks. We proposed it. In 2 weeks, they changed the law. Yeah, exactly. So that was quite interesting. And I say, okay, that's in a certain way as well something to discuss about. In such, I learned the term non-elective system. In such a non-elective system, sometimes the decision kind of times are much shorter than in a democratic system. And one of my provocative statements I always give at my talks is, we really have to think if the challenge of climate change we are able in a certain way to face with our slow speed democratic system, or if we don't need in a certain way what people call an eco-dictator, a dictatorship to turn the wheel. Because it looks like, and I just gave a talk last week on the energy of the future, the first message that this planet is going down the road was 1972, the Club of Rome report. Come on, we are now in 2013 and nothing has changed. We are just spending more, pushing more out. It looks like, so I think that's definitely a valid question to put it, if we are not in a situation where at certain times we need hard decisions, and if we have enough time left, if the planet has enough time left, in a certain way to get these changes. Okay, that's the layout, how the city then should look like. So that was the master plan. You see the rows of windmills at the edge. Mainly the roofs were covered with photovoltaic. There are some, this is the university, some cultural center. The city being mainly on one level in respect of height. That's the dense cities, and you see it. This is where the vision was for the photovoltaic hovering over. So this is the layout of the whole university, of this around 200,000 square meters. That's the 50,000 square meter built today. So they are finished in October 2010, 50,000 square meters. So this is this, and you see this is the platform. This is the 8-meter kind of above the ground, which was as well a problem that because the ground is so badly. Well, the first time when we were on site with a truck, the truck nearly dropped into one of these underground caverns. So they said, better we do this platform. They're still discussing it now because they're spending a lot of money on it. So everything is raised by around 8 meters above the ground. This is where the pedestrians walk, and they have now residences, laboratories, one wind tower to ventilate the city. So this is the animation, and that's the real picture. So they came quite, I would say they came quite close. What is interesting as well, this is, for example, that's the residences. And it was so clear, if we have these narrow streets, what about privacy? So a reinterpretation of the Arabic mashrabiyeh, of this kind of visual protection, in a way which on the other side gives us a lot of accessible thermal mass, because this is concrete, perforated concrete. So this is our thermal mass, which we ventilate at nighttime, which stores the cool of the night to keep the space cooler during daytime. That's the wind tower doing this kind of night ventilation for our outside spaces. Again, so you have some use to look out, but they typically go down the street, so you can't look on the other side of the street right into the face of your neighbor because it's so narrow. This is the light situation indoor, because we get a lot of natural, trying to get as much as possible natural light in. this is the, you see it in the, this is this 50,000 square meters. This is a 10 megawatt photovoltaic system they already installed out of this 150. So they build 1% of the program and around, let's say, 5% of the energy production. So energy, they have enough at the moment. That's not the problem. They find out the problem is the dust in Abu Dhabi. One of their climate points is they have a lot of dust, and everybody's complaining that they have to wash their cars twice a week to keep them white. Now, the dust on the panels is really as well a problem, because after 2 weeks, they lose like 50% of their performance. So they have to clean them every second week, which is a nightmare to clean these big areas. So, and the problem is, in Abu Dhabi, and then we are back to radiation and condensation, because our humidity is so high, at nighttime, all the surfaces, seeing the cold side, drop down, get condensation. So every morning they are wet. And then you get the little dust settling perfectly on this, and then the sun comes out and burns it into the PV. That's the big problem. So we are discussing at the moment with Saint-Gobain, with the big glass manufacturer, if we would put a low-E coating, a hard coating, on the surface of this PV to prevent the long-wave radiation with the sky, we can keep it warmer. So in a certain way, it would not run in condensation. In a certain way, we would get the dust on it, but in a dry form. And then we're talking with a little guy who invented a little robot cleaning this with pressurized air. Because no, you don't have water, you cannot clean it, or you would be needing to clean the whole surface in 1 hour in the morning when it's wet. There's no chance to do it. So this little robot then can run for hours here and just use pressurized air getting the dust from the panels, as long as you prevent that it doesn't run into condensation. Which, on the other side, if you would put a low E on it, at daytime, your PV panel gets a little warmer because you're losing the ability to re-radiate heat against the sky, which means whatever. If you go to polycrystalline, it would drop more in performance. This maybe support you go more into amorph because it's much more temperature stable than polycrystalline. So I think this as well shows that first he said, just put the PVs there, it's done. You have such a lot of sun. It's not done, because if you wouldn't clean it, after 2 months, you would be down at 10%. And then you would run out of energy. And it rains like twice or 3 times a year, so that's not.
So how many megawatts are required?
150.
For the
150. 150. So that's if finally this 3.8 hour sizing was 150 megawatt. And most of it, like 80%, were on photovoltaics. So they, in a certain way, that's a big chunk because this is 50,000 square meters out of 3.8, which is close to whatever, 1.2% of the whole program. But the 10 megawatt out of 150 is much more. So at the moment, and they're covering as well a much bigger site than, in a certain way, this little chunk of buildings, which is standing there. So at the moment, this is not a pair development, but we made as well clear that was our recommendation to do the sizing of this at the beginning so big, because we said in the beginning as well during construction, when you're now starting to construct more of the city, you need as well energy. So production energy is as well something to consider, and you make bigger experience with a much bigger plant with a smaller. What is interesting, they find out in this kind of realization, and if I go back to the picture, that the investment for the substructure of the photovoltaic nearly killed the whole budget, because the substructure is more expensive than the PV panels. So that is created the biggest discussion to say, shouldn't we solve it all on ground, because it's much cheaper to install it on ground. But then you again in the struggle, you would need the rest of the site outside of the city to cover with PV to feed the city if you don't do it on the roofs. So quite interesting. I think it's interesting, and that's I think what I think is, and Masdar, you may have heard it's struggling. They are struggling. They finished this 1% or 1.2%. There is Siemens building their Middle East headquarters there at the moment, and the IRENA, the international kind of energy agency for renewable energies, is building their headquarters there. But out of this, the activities are quite limited because after 2008, UAE kind of said, we have such a lot of empty spaces. So they are struggling as well. But I think there's a lot of lessons learned we can draw out of Masdar City. So this is Abu Dhabi today. If you look at with the infrared camera, and that's not the hottest day of the year, this is 37-degree air temperature outside. You see the asphalt is close to 60. You can imagine you walk over this street, and if you put another 10 degree easily, that's not very nice. So that's now the same. This is 39 air temperature. This is in our little, and this is only a little part of the city. So in a certain way, we are 6 degrees below the ambient. So that's what in a certain way we could prove that. And finally, I think if the city gets bigger, the impact, because they are still in a lot of, just around, if you go here around the corner, then you're out of the city. So there is kind of infiltration of hot air coming in, but we could prove that this approach really works. This was the approach to look at the residential number. The reference they gave us for a typical residential project in Abu Dhabi would be around 400 kilowatt hours. This is all recalculated to electricity. So this is kilowatt hours electricity. Around 400 kilowatt hours electricity for running a typical apartment in Abu Dhabi, including desalination of the water, waste treatment. We designed it for 65. So that was our target. We measured in the first year, or they measured 100. Which I think, and if you saw Thomas' numbers yesterday, probably from Manitoba Hydro, which took like 3 years to get it to the limit, I think this is quite even, that's a very good message because they were like 100% above it in the first year. I think that's quite good. In a certain way, it's quite interesting. Politically, they are not very interested to share the numbers because kind of they want to keep the mist of Masdar City and of the Masdar Institute of Science and Technology to attract as much people from outside as possible because this is an education business. So, but I think in a certain way, we know one of the professors now teaching there, and we got the numbers through him. So I think it shows us we are not yet there, but the direction is definitely the right one. I think the question would be what they're discussing at the moment, if they would keep this kind of podium. Siemens is already building on ground, not on the podium. So it's kind of it will change. But I think all the lessons learned in the process, this part of the city was built in the process of developing this. It took us like a year for the master plan, and then another year to defend it. Yeah, it was like, this is kind of interesting. They decided after we delivered the master plan to give the next phase to W. Atkins, which is a big planning company, British-based, but very active in the Middle East, to do this, the kind of this BOD, the base of design work based on the master plan. And the first thing they did, they kind of put our master plan in pieces and that this is not working, this is not working, this is not working. It took it, and then we had a 1 week kind of review meeting where we were there to defend our master plan and they were there. And luckily they were so stupid that didn't even read. They had like 3 months to read 2,500 pages of a work of a team of like 10 different companies. And I said, in 3 months, they don't get it. That's too short. It will take longer to really dig into the depths. So finally, the team was re-engaged, the Foster team. But the client, in a certain way, is quite kind of, let's say, weak in his decisions. And then they changed the whole heads of the project. And one of them we had last year at our anniversary. He's now a private consultant. So I think there's no big line behind it. There are big political decisions behind it. There's always family politics in Abu Dhabi. But I think we can learn a lot. And that's why I'm really thinking for us, being aware that we never did any city before this, we learned a lot and pushed us a lot into other designs. And Thomas showed you yesterday Pittsburgh, all this kind of work kind of then settled out of this. there was a big question, who would go as researchers to Masdar? And McKinsey did a questionnaire in the first row, in the world's kind of first row education or research entities. And they asked people, would you go to Masdar and to Abu Dhabi? The first question, would you go to Abu Dhabi to do research? It's tax-free, you would earn 3 times more than you earn here. And they got only 25% people interested. And then they said, what if you would go to Masdar, the first carbon neutral city of the world, being a lab on its own? They got 75% of the researchers being willing to go to Masdar. So the attraction, and that was as well is a very nice point in Masdar I always use, because it was so fascinating to see Masdar. We won the competition, I think, in February 2007. In half a year, everybody knew about Masdar city. Now, and people said, how did the UAE guys, how did they do it to get it into all teams? I think the point, my interpretation is, Masdar city provided a try for a solution. So it was not only mentioning, guys, oh, this planet is going down the hill, we are losing, our planet is heating, we are so badly. No, someone said, let's take 25 billion and do it. So for people being always told, my God, we have a problem, people felt like, oh my God, finally someone who says, let's do something. That was the very positive message Masdar brought when everybody was listening and said, my God, okay, we all know we have a problem, but it looks like nobody presents us solutions. And I think that was the very positive message out of this approach, and it created such a big pace. We kind of got this project in Toronto, in Paris, they are trying to do it. In Germany, in the Ruhrgebiet, one of these little villages is now approaching to reduce at least the carbon footprint by 75%. So it created a kind of, I think some German politicians felt like blamed that they only talk very respectfully on the sheikhs, that the sheikhs are doing this and that we high sophisticated kind of Europeans are not doing it.
Became one of the most interesting destinations for architects and planners all over the world. But I guess there is some few cities have been done here, has been built here in Germany before Masdar city, like Vauban and Freiburg?
Vauban, but even before. Vauban was even before Masdar city, but Vauban, let's say, it's, I would call it a low energy city. Even it's not so, it's more in respect of how we define an urban society of the future. A lot of the sites were given to people with low income to build their own houses. It has a certain ecological level you should fulfill. Freiburg, and I think in one of your days when you are here for 1 year, you definitely we should definitely travel to Freiburg because it's the greenest city. Had the first green mayor. Now Stuttgart had the second. So it has as well, there is a society in Freiburg which supports this. And this is why Vauban, being an old French military base with empty spaces, was changed into a new society. And thinking about this was kind of a push as well on the ecological side, but as well on the social side, how we should live in the future together in a city. And this is where Vauban got a big name internationally. But carbon-wise, I would say maybe it's 20–30% below the code. They are not. It's not a passive house, not even or zero energy development. At least on the paper, I know there's a team at Foster's working on the first 25% of the city. There are these 2 projects under construction, but it was as well interesting. Like the IRENA headquarters, which is as well the energy ministry, was widely published this kind of design by Adrian Smith-Gill, which had this kind of cones in it, this big. They're building a totally different building now. They finally called in Wood Badgett from Australia, as well active in the Middle East, and they designed a building which looks a bit different. I don't know if it's as energy efficient as the other one was, but this is what they're building now. So I think, and what I think they are missing partially is someone, and the guy who, I think, the rumors are there was a Lebanese guy, Khalid Awad, who was working with in Beirut for a long time and then moved to the Middle East. He was the guy who had the idea, who told the Sheikh that would be an approach, showing the world that you can do it. And the Sheikh said, great idea, you do it. So he was running this for the first 5 years. And then he quit. Or they kicked him out, there were rumors, he took money, whatever. I think he was a great guy, he had the vision. And then now they have an Australian guy they hired to run this job. I don't know if you can, in a certain, you need someone who really has a vision to do this and has as well the connection to the top guys to get the decision through. So I in a certain way, I would doubt if they will build it to the end. Hopefully they will continue, and hopefully they will as well continue to learn. My discussion with Khalid, we are still connected to him, he's back in Beirut, is we should sit down and write a book on all the lessons learned in this kind of 3-year process. Because this would be the right point to distribute to the world, that everybody should learn it and not make the same mistakes if they start the second master. They can learn our lessons and go there from there on. Yeah.
I was wondering, I think that the top design approach, like when you go from top to down, that approach of design goes with most of the buildings fine, but when it comes to the city with all of sophisticated, complicated layers of socio-economical issues.
Yeah.
So what you did, I was wondering if you are forced to thought of sort of a policy or strategy to respond to the ongoing socio-economical changes and also the development taking place in your technology and your science as well.
Yeah, it was kind of intended to say, okay, we're defining this kind of base of design. Each plot, depending on its type of development, housing or office or laboratory, should have its specification. But in a certain way, we would do a recommendation for the design team because it's clear it was not going to be Foster. There would be architects from all over the world coming there designing for certain companies these buildings. They would get in a certain way a kind of a framework they need to work in. But we said they can come up with their own proposals, with their own ideas. After each design phase, they will get a check. So we will get the materials, we will review it, say if they are online of the target, if they are out of the target, how far they are out of the target, do they need to resubmit the same phase again because they're too far, or if they are in a certain kind of difference, say, okay, in the next phase, make sure you're looking at this and this and this point to make it out. They never set it up. We did proposals, Foster, the whole team did this advisor proposals. They never set it up. I don't know why. It was then the time, and it was 2008, 2009, when finally then as well, the total leading guys in the Mazda company changed. And then it became quite untransparent for people from the outside. The only then point is to get information is a personal contact. And that's one contact we have of one of the professors who was at Mazda, who is now a professor at the Mazda Institute of Science and Technology. So that's our level of information we're getting out there. But it's kind of, I think it's such a big development. There's so many interests. There's so much money in it. And in a certain way, we are such a small group. Yeah, so we can say, okay, let's learn as much as possible, take the pace, tell other people, look, the sheikhs are doing it. Why are you doing it? And Thomas was quite successful to get the mayor of Toronto into it. Said, guys, the guys are doing it. Let's do a 300,000 square meter development down at the lake, zero carbon. They now do it. So in a certain way, we used it to tease other people. That's the only possibility.